Hi everybody, I hope that all of you are doing well. This is lab number 4, and in lab number 4 we will learn what is the oscilloscope, and we will use the oscilloscope to figure out the root mean square voltage, or V root mean square. Also we will use it to figure out the frequency from the function generator. And also we will use it, guys, to study some figures called Lissajous figures, and I will tell you what is the importance of these figures. Let's see, what do we need for this lab. We need some coax cables, we need oscilloscope, we need 2 function generators, we need a voltmeter. We need it to figure out the V root mean square, the voltage from the function generator. And just, guys, to let you know that the function generator provides us with AC, alternating current. So when we use this voltmeter, we need to adjust it to give us the voltage reading for AC mode. And some banana cables, of course, we will need them. Okay, so this is everything, guys, that we need for this lab. Okay, now what do we need to do? We will turn on the oscilloscope, as you can see right here, and turn on the function generators. Actually, in part number 1 we will use just one function generator, so we won't need this one, so we'll use this one for part number 1. Okay, so as you can see, guys, the first thing that I will do, I will connect one coax cable right here, and the other one on the other side right here. Now I will give you guys a close look on the oscilloscope. So here's the oscilloscope display. Actually, guys, what we will use here some of these keys. We won't use all of them. So the first one that I would like you to use is to control the voltage division. So what I will do here, I will control the voltage division. As you can see, we know that the function generator provides this connection with the voltage, but here we can multiply the function generator voltage with some numbers, so we can increase the voltage, as you can see. And the other thing that I would like, guys, to know is we can control something called time division. So what is time division? So the whole axis that you see right here is called time axis, and the axis that you see right here is the voltage axis. So when we control the voltage division, the time division, as you can see, so we can control this wave that you can see. So why do we have wave here? As I mentioned, the function generator provides us with AC voltage, and the AC voltage continue to alternating, go ups and down, go ups and down. And also, guys, we can move this sine wave, so we can move it forward or backward using this knob right here. The other knob right here can move it ups and down, ups and down. Now here we have function generator, and what is the job of the function generator? The function generator can provides AC signal, and this AC signal has a voltage, peak-to-peak voltage, and also has frequency. So all of these buttons that you can see can provide us with different frequency. So here you can see that we have max 2 Hertz. Here we have 20 Hertz. Here we have 200. Here we have 2000, 2K, 20,000, 200,000, 2 million, 20 million, or 20 megahertz. So this is one of the things that you need to know. The other thing that you need to know, guys, are these buttons here. So using these buttons, we can control the shape of the signal. I will show you that. So as you can see here on the oscilloscope, we have sine wave. So if we change this signal shape from sine wave to this square wave, so you can see that we don't have sine wave anymore, so we just have square wave. We can also change it to be triangle, as you can see, like this. So this is one of the functions that you can find in the function generator. And also there is another thing that you can control, which is, let's go back to the sine wave. So the other thing that you can control is the peak-to-peak voltage. So the distance from here to here with respect to y-axis is called V peak to peak. So this is the voltage from this bottom peak to this top peak. So this is called V peak to peak. And it is possible to control it by changing this knob right here. So we can increase it, as you can see, so that's possible. Increase or decrease the peak-to-peak voltage. Okay? Yeah, so that's great. And also, guys, I would like to give you kind of general use for the oscilloscope. So this oscilloscope can be used to measure voltage, AC voltage. It is similar to the avometer, similar to this one. But this one is more precise, so it can give you precise numbers under high frequencies. Yeah, so this is kind of equipment that can professional people use it to measure the voltage. Okay. So how to measure the voltage? As you can see right here, we have a signal. It is sine wave. And as I mentioned, guys, we can move it forward and backward, as you can see, using this knob right here. That's great. And also we can move it upward and downward. But let's center it. This axis, as I mentioned, represents the voltage. The vertical one, and the horizontal axis here represents the time. And you can see that this time axis divided to small divisions, those squares that you can see. Each division here, let's talk about this particular case. So its division here is equal to 5 volt. Sorry, it's equal to 400 microseconds, since we are talking about the horizontal axis, the time axis. So each one of these divisions, 1, 2, 3, those squares is equal to 400 microsecond. Let's see now what is the time for 3 divisions. So we have 1, 2, 3 times 400 microsecond. The same thing is applied to the vertical axis, the voltage axis. So you can see also the vertical axis is divided into small divisions, 1, 2, 3, 4. And its division here, each volt division, is equal to 5 volt. So let's count 3 here, 3 divisions, 1, 2, 3. So how much voltage do we have here? Actually we have 1, 2, 3 times 5 volts, so that will give me 15 volts. This is how can we, guys, count, and you can see that count the voltage and the time. And also you can see here that each division is divided into small spaces here. So 1, 2, 3, 4, 5, 6. So that can give you great help to figure out more precise numbers. So let's count, for example, 1.5 divisions. So this is 1 division, like 1 square, 1 division, and a half. 1, 2, 3 and a half. So this is 1.5. 2.2, 1 square, 2 squares, 1, 2. The first sign here. So we have 1, 2.2. So we have 1, 2, and here we have 0.2. So that means we have 2.2 voltage. So this is how to measure the voltage and the time using the oscilloscope. So what I will do right now, guys, I will use the example that we have right here, and in this example I will try to measure the peak-to-peak voltage and see how much voltage do we have. So I will adjust it and see how many squares do we have. So we have 1, 2, 3 squares times 5 volt. This number right here, which represents the division, the voltage division, it can be changed. So yeah, we can have 2 volt, for example, or yeah, you can choose the value that works for you. So that's fine. So you can change it. But for me, I chose 5 volt. So we have 3 squares, 1, 2, 3. So we have 3 squares times 5. So that will give me 15 volt. Now let's move it up and center it and try to figure out the time. So the time, guys, it is similar to what we studied in classical mechanics. So the time, since this axis represents time, to figure out the periodic time, you need to count from this peak to that peak, or from this peak right here to that peak right here. So that will give you the periodic time. So let's write that down here. So V peak to peak in this case is equal to 15. I wrote it down, 15 volts. And then let's see the time. So here, from this peak to that peak, I can move this a little bit up, so, or down. Yeah, so that can help me to get precise number. Yeah. So let's follow now the horizontal axis. So we have 1 square, 2 squares, 0.1, 2, 3, 4, 5. 2 squares, so we have 2.5. So 2.5 times this time division, which is 400 microsecond. So this is the periodic time here. So 2.5 times 400 microsecond. This is the periodic time. Now I will show you the numbers that we got and the reason of extracting them from here. I'm talking about the V peak to peak, and the periodic time. Okay? Okay, now I will explain to you guys why did we measure the peak-to-peak voltage and why did we measure the periodic time. So let's see why we did that. As I explained to you, the peak-to-peak voltage represents this volt value from this peak to this peak. I'm talking about the vertical axis. So this is called V peak to peak. The periodic time, or T, the time for one cycle, the time for one cycle is from this peak to that peak. So this is T. And what we did, guys, we could manage to find T. So T was 2.5 divisions times 400 microsecond. This is the time for one division, and we counted 2.5 divisions, if you still remember that. V peak to peak, we got that, and it was let's double check the number of divisions. I believe we got 3. Yes, 3 divisions. Yeah, so it was 3 times 5 volt. So this will give me 15 volt V peak to peak. 15 volt V peak to peak. Now let's check the periodic time. The periodic time, or the time for one cycle, is equal to 2.5, the number of divisions, times 400 microsecond, and that, guys, will give you 0.001 second. Again, similar to what I mentioned, guys, in classical mechanics 211, we know that the frequency has a relation with periodic time. If we are talking about like alternating wave, like sine wave or cosine wave. So we know that the frequency is equal to 1 over t. This is the definition. This is a simple definition. We got that from Physics 211. We studied that, guys. When we studied the simple harmonic motion and the harmonic motion in general, so we know that the frequency is equal to the reciprocal of periodic time. So now, to get the frequency, we need to have this value and get the reciprocal for it. So to get the frequency, we need to have 1 over 0.001 second. So that will give me 1000 hertz, or second to the power minus 1. So we know that. Great. So we got the frequency. This is the first thing. So that's great. Now I would like to move to the voltage, or V peak to peak. So why do we need V peak to peak? V peak to peak, guys, was 15 volt, and V peak, which is from here to here, so this is called V peak, and V peak is equal to 15 volt divided by 2, so that will give me 7.5 volt. So this is V peak. Now guys, I will come to the most important thing in this part, which is calculating the V root mean square. So V root mean square here is equal to V peak divided by square root of 2. So what is V root mean square? Actually guys, this is the value that you can see here. This value that you can see here, it can be measured using the oscilloscope. But this value, V root mean square, it can be measured using this multimeter. So this multimeter will give us V root mean square. However, the oscilloscope will give us V peak to peak. But from the oscilloscope reading, or from the oscilloscope voltage reading, we can get V root mean square simply by applying this equation. So we need to divide V peak to peak by 2 and then divide it by square root of 2. And what we will get? We will get 5.3 volt. So this is V peak to peak. Now let's check if the frequency that we got here is correct, and also check if the V root mean square that we got here is correct. So let's see what do we have, guys. Okay, so this is the moment of truth. So let's see what do we have. So what I will do, I will compare the 1000 hertz that we got. So we calculated that from the oscilloscope information. You know that we got the periodic time, and then we give the reciprocal of the periodic time to have the frequency. So here we have 1000 hertz. And if you look here, you will find that we exactly have 999, which is around 1000 hertz. So that's great. There is error, and that's possible, but no problem with that, since we have like close number, so 1999. So that's great. Now I will check the V root mean square and see. So from the oscilloscope data we got 5.3. Now what I will do, I will use the multimeter that you see right here. So I will use the multimeter to double check if we have this V root mean square value. So what I will do now, I will try to connect the multimeter, as you can see. So we need banana cables, and also we need this coax cable. So I will have it connected here. With this function generator. And now what we will do, guys, we will see the voltage that we have here. So let's see what do we have. Okay. Yeah, so you can see the root mean square value, guys, here is 5.24, which is close to 5.3. So the conclusion here, we could manage to use the oscilloscope to figure out the V root mean square, and also we could manage to use the oscilloscope, guys, to figure out the frequency that we have on the function generator. Okay, so this is one part of lab number 4, and there is another part, guys, which is related to something called Lissajous figures. I will show you Lissajous figures, guys. You don't need to do any calculations. Just I would like to show you that, and how to display XY mood, and how to display the sine cosine wave mood. So yeah, so we are done with this part, which is great. let's now move to the next part. Okay, now this is part number 2 of lab number 4. And what we will do now, we will use another function generator. So in part 2 we will try to have just one period on this screen. And actually guys, once we get that for the signal from this function generator, we will do the same thing for the other signal from the second function generator. And before we start, I would like to mention that this oscilloscope can show us 2 signals at one time. So let's do that, guys. So we'll start this. So it's not 1000, so we'll try to decrease it a little bit to have around 1000 volt, 1000 hertz as frequency. Yeah, now we will go to channel number 2. This is channel number 2. And try to fix the coax cable and have it fixed right here. This is the output, similar to this output. Yeah, now we have 2 function generators, but we need to maintain this frequency around 1000. Great. I will show you the other wave, this one. And actually you can see here that the voltage division is 100 millivolt. We need to control that and drop it down to be around, exactly, to be around 5 volt. So both of them have 5 volt. And you can see that this wave is drifting to the right. Hopefully that's clear. So you can see that the blue one, the blue wave, is drifting toward right. Actually, we can prevent that by controlling the frequency. So we need to have exactly the same frequency on both of these function generators. Okay, so now we have this function generator working, so that's great. Now what I will do, I will remove this signal and continue to work with the yellow one. So what I will do, simply, it is not that hard, guys. What I need to do, I need to have like one period. So this is one period from this peak to that peak. I need it to cover the whole screen. So what I will do, so firstly I will change the voltage using the voltage division. Just have it 2 volt. And then we need to control the frequency so we can stretch this wave. So let's do that together. So this is channel number 1 with this oscilloscope, or with this function generator. So now I will decrease the frequency, and you can see how we stretch this wave. Control it. So the goal is to have just one period covering the whole oscilloscope monitor. Okay. Continue to decrease the frequency. Yeah. So you can see now, guys, this shape. So what we did here, we just focus it on one period. So we don't have the whole oscillations, the whole signal that we had before. So right now we just have one period. Okay, so this is what we will do with the other with the other signal from the second function generator. So I will have it here, but you will notice that it will not be stable and clear anymore. So let's do that. So you can see that. So it's not stable and clear anymore. So what we need to do here, we need to have the same thing like this, and then decrease the frequency from this function generator to have the same number here, 253 Hertz. Yeah, decrease it. So when those two frequencies match each other, so you will notice, okay, should be 253. I will now use this. Yeah, so it is around 253. Yeah, so you can see, guys, it is sometimes hard to stop this signal, the blue one, but now we can see that that we can have one. Let's wait for some time. So we can have just one period, guys, as you can see. Yeah, so this is a way, guys, to focus on one period from the whole signal. I prefer to show you that. Let's keep going. Okay, now, guys, we will study Lissajous figures. This is the last part in this lab, lab number 4. And to do that, guys, you can see that we are using the sine wave mode. So what I will do now, I will move to XY mode. So it will have channel 2 represented by x-axis and channel 1 represented by y-axis. And let's see what we will have. So we'll have this kind of figures. Actually, guys, we can move here and make it a little bit smaller by controlling this. Yeah, so we can have it a little bit smaller. So if we have a circle, as you can see right here, so what does that mean? That means the frequency from this function generator is equal to the frequency of this function generator, or from this function generator. So why the circle is moving? So why it is rotating, as you can see right now? So the reason, guys, because there is phase difference. So you can see that the blue signal is drifting. It is moving toward right. However, the yellow one just fixed, stay at the same position, never move. So that's why, so when we move to XY mode, we will see this Lissajous figure. And actually, guys, we can control this figure. So what we will do right now, maybe we can try to increase the frequency. So here we have, let's see, so this is channel number 2, this is channel number 1. Okay, so what I will do, I will make channel number 2 twice frequency than channel number 1. So let's see what will happen here. So 253, I will have 506. So let's see what we can have here. So 500, I will control this. So 500. Sometimes hard. that's great, I believe. So now we can get just 506, and you can see here what's happening, guys, here. Yeah, so this is what you can see, guys. You can see that channel number 2, we can see that the signal is oscillating twice than the signal from channel number 1. We can make this frequency 3 times higher than this frequency, and let's see what we will have here. So 250, so we need to add here, we need to add 253, so that means we will have, so 5, 6, 7, so 759. We need 759, so we will do that. So 759, we will try to do that. Yeah, so you can see, guys, so how many modes here. So the horizontal modes are 3 and the vertical modes is 1. Yeah, and actually Lissajous figures, guys, are very important. So using this technique you can figure out the frequency. For example, if you don't know this frequency right here, so you can just using this to figure out the frequency of the other function generator. So let's assume that we don't know this frequency. So by looking here, guys, so we can see that channel number 2 is oscillating 3 times than channel number 1. And by dividing the 758 or 759 by 3, we will get this number here, which is 253. Yeah, let's make this 506 and see what will happen here. So we'll have another different so you can see that guys, so this channel oscillating twice and this channel is oscillating 3 times. Yeah, and those Lissajous figures can be more complicated. I will make okay. Okay, so channel number 1 is X. Yeah, channel number 1 is X, and channel number 2 is Y. Yeah, so here's channel number 2 and here's channel number 1. Yes, yeah, I'm sorry, so just the opposite, channel number 2, channel number 1, and we can see that channel number 2 is oscillating 3 times and this channel is oscillating 2 times. Here I mean 2 times 253, and this is 3 times 253. Yeah, so these are Lissajous figures. So what I will do right now, I will give you kind of close picture so you can see. Yeah, this is Lissajous figure. I won't go deeper in this, just I would like you to know that. And this is the frequency for channel number 1, channel number 2, I'm sorry, and this is the frequency for channel number 2. Let's see, this is 1, this is channel 1, and this is channel 2. Yeah, great. So this is kind of a simple illustration, guys, about how to use the oscilloscope. It's important to know how to use it. Also how to use the function generator. So the function generator simply is a power supply, but this power supply just gives AC current, alternating current. It's different than the regular power supply or the DC power supply that we used before. So this is a DC power supply. Yeah. And this function generator is different. Yeah, it gives AC current. Yeah, so this is everything, guys, about today's lab, and hopefully it is clear. If you have any questions, don't hesitate to email me. So thank you so much, and see you next lab.